you can express this in two ways. One option is to write dA, which is the derivative of the surface area of a cylinder, dr. Okay, so dA by dr. So what this is saying, I know you guys are used to y's and x's, but there's nothing special about the variables y and x's. It's just typical in mathematics to use those letters to represent the independent dependent variable. Here our dependent variable is the area, and the independent variable is the radius. So you could represent the derivative in this way. You can also represent the derivative in this way using prime notation. Whichever way you use, the derivatives is going to be, we're going to find the derivative with respect to r, okay? So 2 pi is just a constant. This is our variable of differentiation. So you could just bring the 2 down. So it'll be 4 pi r and subtract 1 from the exponent. And then in the same way here, we're differentiating with respect to r. So just bring the negative 1 down and then subtract 1 from the exponent. Okay, so that's our derivative. I'm going to write the derivative in a way that maybe looks a little bit nicer. So we have this, if we write it with positive exponents, and then if we combine the two fractions together into a single fraction, we get 4 pi r cubed minus 700 divided by r squared. Okay, and so now we have our derivative. Now, remember what our goal is. Our goal, don't forget the goal. These optimization problems are so long that you can forget what the goal is. The goal is to minimize the surface area. To minimize the surface area, you're going to have to find the stationary points. To find the stationary points, you're going to have to set the derivative equal to 0. Okay, so I'm going to say something along the lines of, I'm going to say at stationary points, a prime of r is equal to 0. Okay, now the derivative will be 0 when the numerator is 0. The denominator is always going to be positive because the radius is bigger than 0. By the way, I should have actually mentioned that earlier. As soon as you express the area function, surface area, in terms of r, you should state the conditions for r here. So right now, if you think about a cylinder, and you think about a cylinder that has a fixed volume, the radius can't be 0 and it can't be negative. It can't be negative because radius is the length. If it's 0, the cylinder almost like collapses into like a line segment or something. And the radius can't be 0 then, and it can't be negative, so it's got to be a positive value. Now, the other thing you might want to consider is there an upper bound on that positive value? So am I allowed to make the cylinder with a radius as large as I like? And the answer to that is yeah. Like as you make the cylinder, as you increase the cylinder's radius more and more and more and more, the height's going to drop because these two have like an inverse relationship. And so it's okay to have a radius that's positive, and it doesn't have an upper bound. It can be as large as it likes because the volume is fixed, so the height will compensate. As you make the radius bigger, the height will kind of get smaller and smaller and smaller. Okay, so going back to this, the derivative will be 0 because this is always positive. So the derivative will be 0 and the numerator is 0. And so we have something like this. And the next thing we can do is we can solve for r. So r cubed is going to be, if I add 700 and divide by 4 pi, I get this. And if I take the cube roots of both sides, I get this. I'll just make that a little bit neater. So that says 700 divided by 4 pi, and then the cube root of that. Now, it's important to realize, I know with calculus, we're going to be only dealing with real functions with real inputs and real outputs. Calculus with complex variables is way beyond the scope of HL math, but I still think it's important to remember things that you've learned in the past. This is something cubed equals something. So this is actually going to have 3 solutions, but 2 of those solutions are going to be complex solutions, okay? And so here we only care about the real solution because we want a radius value. So the real solution that we get is the cube root of 700 divided by 4 pi. And that's approximately equal to, if you crunch that in a GDC, 3.82 centimeters to the nearest 3 significant figures. Okay, so you have a radius value, and oftentimes people kind of stop here. They see this radius value. They're like, oh, well, I have my radius. I can just take this radius, plug it back into my relationship between h and r, find height, and I'm done. But that's not the right approach here, because this radius, so I'm just going to draw you an example graph here. So here's the area, here's the radius. This radius, like, you don't know. It could be a minimum, it could be a maximum. Like, you don't know if it's a minimum, maximum. You have no idea. And the reason you have no idea is because it just tells you it's a stationary point. So it doesn't tell you what's happening in the locality. To decide what happens in the locality, you have to look at the sign chart of the first derivative. Okay. So let's do that. Let's look at the sign chart. So our goal is to now classify this stationary point. Okay. So I'm going to say a prime. Maybe I'll use Leibniz's notation actually. So I'm going to say dA by dr, which is the derivative of the area function with respect to the radius, has a sign chart that looks something like this. Now remember, we're only considering positive values for r, so r equals 0 is undefined, and values to the left of 0 are also undefined. And we want to kind of figure out, hey, what's happening to the sign of the first derivative? Because if the sign of the first derivative is going from negative to positive, we have a local min, and that's what we want. If it's going from positive to negative, then we have a local max, okay? And that's not what we want. We want to minimize the surface area. Okay, so we know that we have a critical point, or we have a stationary point at r equals cube root of 700 divided by 4 pi, okay? So that seems to be important. We know that that value leads to 0 for the first derivative, okay? Because we solved this equation here. What we need to do is test the value to the right and test the value to the left. You could do this using a calculator, but say that you didn't have a calculator, you kind of have to choose a value that's bigger than this. So if I call this, I don't know, R1, if you choose an R value, maybe let's call it R2, an R2 value that's bigger, you can maybe choose something like the cube root of 800 divided by 4 pi. The cube root of 800 divided by 4 pi is strictly larger than the cube root of 700 divided by 4 pi. Okay, so you would take this value and you would kind of test, you test the first derivative. Okay, so maybe you test this simplified version here. So what you would do is you would say something like, when the radius is, maybe I'll just say r, when the radius is the cube root of 800 divided by 4 pi. Okay, so imagine plugging in this value into here. Once you cube it, the cube root's going to disappear. The 4 pi and 4 pi here are going to cancel. And then what you have is 800 left over. 800 take away 700 is going to be 100. 100 divided by a positive value is going to be positive. Okay, so what I'm saying is when the radius is this value, the first derivative is positive. Okay, I'm going to get rid of all this. Okay, so that means to the right of this value, we have a positive sign, or positive first derivative, and you can confirm yourself by testing a value using a calculator, whatever you like, that to the left of this value, you have a negative sign. The first derivative is negative. So here's the situation. The situation is the function seems to be decreasing, and by the function I mean the original surface area function. The original surface area function seems to be decreasing and then increasing. That means that this point here is a local minimum. Okay, so you could say something like, therefore, at r equals, I'm going to use the approximate value. At approximately r equals 3.82 centimeters, we have a local min. And this is very important to do because the question's asking you to minimize the surface area. So you have to make it clear to the reader that you found a local min, and you have to make a sign chart of some kind. Now, this does not guarantee that this is the absolute minimum. In this case, it kind of does actually, because you only have a single interval of decrease and a single interval of increase. So the function's always decreasing to the left, always increasing to the right. So that means you know this also happens to be the local and absolute minimum. But let's say that you wanted to test the endpoints. Now here you don't really have endpoints, right? Because look at the function here. We have the radius is positive. And so the question becomes, well, if the radius is positive, what's the lower bound and what's the upper bound, because this interval is not really bounded. And here what you have to do is you just make a limiting consideration. And I think for the purposes of HL math, you don't really have to write this down or anything, but you can maybe just think about it. So as the radius, let's consider the upper bound. Let's consider what happens as the radius goes to infinity. As the radius goes to infinity, okay, so as the radius goes to infinity, the area function is going to infinity as well. Okay, because as the radius goes to infinity, this part's going to go to 0, but this part is going to go off to infinity. Okay. Because as r goes to infinity, r squared goes to infinity. Now, as r goes to 0 from the right-hand side, okay, because the radius has to be positive, the area function, this is where it's a little bit tricky. So you kind of have to look at, maybe I'll write it in this form. It's a little bit easier to see it in this form. So as the radius goes to 0 from the right side, this part's going to go to 0. Okay, so as the radius goes to 0, r squared goes to 0, and this goes to 0. But as the radius goes to 0 from the right-hand side, 700 divided by that small positive value is actually going to go to positive infinity. So I guess what I'm saying is you're going to positive infinity as r goes to 0 or as r goes to infinity. So even though we don't have endpoints, we can still do an end behavior analysis, okay? And the end behavior analysis seems to suggest that the area, the surface area, is going off to infinity. If you try and picture a cylinder with a really thin radius, with a fixed volume of 350 milliliters and a really thin radius, it's going to be like, the height's going to kind of compensate so that the volume remains fixed, and the surface area is going to be extremely huge on either end. Okay, so hopefully that kind of like in the picture that you have in your mind kind of agrees with this end behavior analysis. Okay, so we can say that we have a local min, and we can say this is also the absolute min. Okay.